Hello, everyone. Today we're going to talk about direct fixation track history and development. Um, this is a joint presentation between LB Foster and CTA. Presenting with me is Matthew Gibbs, civil engineer from CTA, and myself, Sheen Fong, engineering manager at LB Foster.
So I'm Matt Gibbs from CTA, and first we'll be talking about some history of direct fixation at CTA and some issues we've had, and then we'll talk about the future of direct fixation track at CTA.
Then I'll be going over the history of direct fixation fastener design at LB Foster, some recent technology developments we've been working on. Then I'll go over some basic DF design and development procedures and also the qualification testing of DF fasteners.
Okay, so let's talk about the little bit about the history of direct fixation at CTA. One of the first examples we have of direct fixation track was in the downtown subways. This would be the Dearborn and State Street subways on the blue and red lines downtown. And these subways were constructed, they were designed in the 1930s and then constructed from the late 30s up through the 1950s. And they used a wooden tie or half tie set into a concrete track bed. And this type of track was only used for non-special track, which is tangent and curve track. So special track work was in ballast, and then this was only for, like I said, tangents and curves. And you can see on the drawing here the general layout of the track. So you had half ties every 24 inches, and then every fourth was extended for the contact rail chairs. They were held into the concrete track bed with inverted screw spikes. And then the track was actually set, and then the concrete was poured around it, similar to a current top-down construction. And then they actually had a fairly advanced track fastening system at the time, and it was a track tie plate with screw spikes fixing it to the wooden ties, and then they had spring clips with a nut on top that held the rail into the fastener, and then they had a rubber pad under the rail for resiliency. And these lasted quite a while, but eventually they deteriorated and were replaced with non-resilient fasteners, typically either a double shoulder plate with spikes or rolled tie plates with E-clips. And this system lasted, somewhere around 50 to 60 years, but eventually it became end of life, and we had to go through some projects to replace it. So in the 2000s, we had several projects that went through to replace the wooden half ties with a more modern fastening system. And at this point, they deteriorated pretty significantly and were basically just at the end of their useful life. So as you can see in the photo here, in this case, they installed temporary rail fastening plates, and then they could use that to support the rail, and while the track was being built. And so they removed the wooden half ties, they set the rail, adjusted the line and gauge, and basically did a top-down construction. Another scheme that was used was to replace every other tie at a time, and then the track geometry was mostly kept the same. So we replaced it with a concrete, poured in place concrete with the Foster F20 R4 fastener on top. And this was all completed during weekend outages. So we had typically a 54-hour weekend outage, and they would do, say, prep one weekend, and then the next weekend they would pour the concrete, and there was a high early concrete, so the ties would be ready for traffic in about 12 hours, and then they would clean up, and we could get trains running again. Here are a couple pictures of the older track system after it had been modified with the rolled fasteners. Here's a temporary fastener that was installed for the construction, and then here you can see some rail-based corrosion behind where one of the older fasteners were. And then on the right, you can see the newer concrete half ties and the new fasteners. So the system generally held up fairly well, but in areas where we have a lot of moisture, we have experienced accelerated degradation of the fastening system. And so within the last few years, after about 10 to 15 years of service, some were even sooner, we had to replace quite a few fasteners in order to maintain the track system. And these areas often experience heavy rail-based corrosion, and then the fasteners deteriorate. So, and then even further, in some areas, the bolts have corroded or broken, and so the bolts can't be removed to change the fastener. And we've more recently been starting to core out and replace those inserts. So you can see here an existing insert, and then on this side, the insert's been cored out. Here's the replacement. So we're using galvanized clips, galvanized bolts, and EON-coated fastener for corrosion resistance. And hopefully this will give us more life. And the next area we'll look at is the OLeary Subway. So that was constructed in the early 1980s, and it was the next direct fixation system that was installed on the CTA. This used lowered fasteners on canted plinths, and it also is the only area where we have direct fixation special track work up to now. The fasteners were mostly replaced with SRS fasteners by Pandrel in 2008, and this area was featured, as you can see on the right, in TCRP Report 71 Part B, which is a experience with direct fixation. And you can see here's an example of one of the fasteners that the anchorage bolt had failed. But so the system generally worked out pretty well, and we've been able to maintain it. And then, like I said, basically the tangent fasteners have been replaced with the SRS fasteners. The special track work fasteners are still the originals that we've been able to maintain. The next area that we did was Addison Station, and that was built or rebuilt, I guess, in 1990s to convert it from a side platform to an island platform. And this was really kind of doomed from the start. So it had substandard installation, and installation is one of the most important parts of a successful direct fixation installation. The track system started to fail fairly quickly, and this was also featured, perhaps an example of what not to do in the TCRP report. And these pictures are from about a year after the construction, and you can see that the fastening system has already started to deteriorate. So we were able to do some maintenance to keep it together, including replacing a bunch of the fasteners with a more modern fastener, I guess you could say. But in 2019, we completely overhauled it. So track one, the plinths were ground down, and we kind of used this as a test bed. So on track one, we ended up grinding the plinths and removing the existing inserts and replacing them with new inserts. In track two, we completely replaced the plinths, and we had intended to replace the plinths on both track 1 and track 2, but contrary to what the drawings had shown, it appeared that the plinths were poured in as part of the deck and not a separate pour. So we had a challenging time removing the plinth concrete. So that's why for track 1 it was determined to try to refurbish the plinth. The contractor came back and proposed the alternative, and that we worked that out. But so right now we're basically testing the installation on a new fastener or a new plinth versus epoxying in new inserts on an existing plinth. And then a little bit more recent than those, we've had direct fixation aerial track installed at Belmont and Fullerton on the North Main or red and brown lines. And those systems have been generally pretty successful. A couple of lessons learned there were that the drainage details could have been improved, and then there are a lot of kind of appurtenances to the track that have blocked the drainage and trapped detritus and stuff like that. So so those generally have been good. And then a little bit after that, in the mid 2000s, we replaced Wilson Station, and that has an aerial structure with LVT dual block track. And so far that's performed well. And then currently we're in the process of a red-purple modernization project, and that's going to be replacing some portions of the North Main line with direct fixation aerial structure. And that will include special track work. So that'll be our next experience, I guess, installing direct fixation special track work. Just to highlight a few issues that we've experienced. One is that installation is critical, like I mentioned. If you have a substandard installation, you definitely will have a shortened track lifespan and increased maintenance. So that's installation is one of the most important parts of the direct fixation track system. The other thing that we've had a lot of issues with, which probably other people have had the same, is that water leaks and moisture severely affect the track system, and the fasteners are no exception to that. So areas where we've had water that's held up around the fastener, or debris that kind of holds that moisture up there, the fasteners will deteriorate quickly. And you'll also have rail corrosion and other problems that dramatically shorten the life of the system. And then another thing is that repairing direct fixation track is not usually a specialty of your track maintenance staff. A lot of them, you know, they're used to maintaining, say, ballasted track or something like that, and they're not necessarily used to working with concrete and things of that nature. So it can be a little more challenging to maintain direct fixation, especially if you need to do more intensive work like coring out inserts and things, because track guys aren't necessarily experienced with that, so you have to get them up to speed. And then, of course, repairs can be time consuming. So coring concrete, epoxying in new inserts, and trying to extract fasteners that have been corroded into place and things like that can really be a slow process, and can really affect train operations, both while it's deteriorated and while you're trying to repair it. So here's just an example of kind of a poor installation. And you can see there's a gap under one of the fasteners here, and the clip's broken here, and just, you know, there's some moisture issues. So these are things that we're trying to address and get cleaned up. So a few points on where we'd like to go next is do better job with installation. So we've really been on our contractors, where we've been installing direct fixation, to be thorough with their installation procedures, and we're really watching that closely to make sure that they do a better job with that. The next thing is dealing with water infiltration. So we've been grouting the tunnels. All of our tunnels are concrete structures, so we've been grouting them, trying to keep the track more clean so that the water doesn't pond around the fasteners or it doesn't hold moisture around the fasteners, and that everything can drain out. And that's always a challenge with manpower and just keeping up with things. And then we've also been looking at fasteners with corrosion resistance. So here you can see a picture of a Foster F51 that we're starting to use, and it has an EON coating on the exposed metal parts so that it improves its longevity in a corrosive environment. And then we're also becoming more knowledgeable about direct fixation as a maintenance organization, so that hopefully we can get the most life out of our system. And you know, track maintenance, we've often not had as much support and manpower as we would like, and so it can be challenging to maintain that knowledge. A few things on where we'd like to go next. So one question that we've kind of talked about is, what is direct fixation? You know, is it just a fastener on concrete substrate? Would our open deck elevated track be considered direct fixation? It's, you know, about 40% of our system is open deck elevated, and it's basically just ties attached to the top of a steel structure. So it seems like we could treat it like direct fixation. It has limited or no resiliency, and the stresses that get transmitted from the rail through the fastening system don't really have a place to go, and it can cause shorter lifespan on the fastening system than we'd like to see. So one thing that we've gone out looking for are fasteners that can fit into the footprint that we have available on the open deck elevated system. And as you can see here with the steel inside guardrail and the timber guard, there's not a lot of space available. But we've been able to the fastener manufacturers like Foster have been able to develop a fastener that can fit in that footprint. So we're looking to test resilient fasteners on the elevated, and hopefully that will help improve our noise and vibration and help reduce the stresses that we see on the screw spikes or spikes, and improve the longevity of the system and make it quieter. And the benefit of that is if the fastener can fit on elevated track, we can use it anywhere. So, and it provides us more flexibility than the current North American standard footprint. So probably where we're going, most likely, is that this fastener layout will become our new standard, because it can be used in all of the different applications that we have where we don't have existing inserts already in the plinths, and it's a very flexible sort of design for us. So with that, I'll turn it back over to Sheen, and he'll go through the Foster.
Okay, so I'll go over the history of DF fastener developments at Foster first. So prior to the 70s, DF fasteners were primarily plate pad systems. These were non-bonded designs. It was essentially a rolled steel plate sitting on some sort of pad. In this picture, prior to the 70s, they were using these what they called tie saver pads, which was made out of an asphalt material. Also, we had some elastomeric molded pads that took the form of the base of the rail and were bolted down in place using steel plates and surrounding the rubber pads. Then from the 70s through the 80s, we started moving towards a bonded elastomeric fastener, as we all know them today. These back in the 70s and 80s were used a steel plate bonded inside the fastener body. And these used what we call a bolt through top plate design, where in the picture to the right, you can see that the bolt passes through the top plate and is insulated using typically a nylon material or some other insulating material to prevent electrical leakage to the rail. These used various bolted rail clip designs or even some spring clip designs, and typical lateral adjustment was done on the rail across the top plate. Then from the 80s through the 2000s, we started seeing ductile iron plates replacing steel plates. These were cast ductile iron plates that had two plates inside a fastener, bottom plate, which was bolted to the plinth, and a top plate, which secures the rail. And these two plates were bonded inside the fastener and were electrically isolated from each other. We saw predominantly spring clips, such as the Pandrel E-clip or the PR clip, and rail adjustment was moved to the entire fastener body. So the rail base remains fixed on the DF fastener, and lateral adjustment is now made through the anchor bolts using a serrated surface that locks it in place. And then from the mid-2000s to present day, we see more focus on improved noise and vibration mitigation. This is either through high resilient fasteners, such as the one in the bottom right picture. We also are focusing on more compact footprints that can be installed on multiple types of track, such as concrete plinth and wood tie tracks. You can see our F51 in the top right. We've been focusing on higher performance coatings that significantly extend the useful life of our fasteners. And also these new designs still maintain the similar construction methods as we saw from the 90s through the mid-2000s, which were ductile iron plates, spring clip housings, and lateral adjustments in the plates themselves. Some technology developments in the DF fastener development industry. One of the main ones is finite element analysis, as software advancements make improvements to our analysis abilities. This reduces our design time. We're able to design and develop fasteners much quicker now, since we can perform an initial development design, run it through analysis, and tweak it as necessary. We're also able to predict vertical and lateral performance of our fasteners before making them. So we'll know if we're in a good place before we spend money on tooling. And we're also able to predict stress analysis in the ductile iron plates, and also predict rubber strains. Some advancements in materials have helped our industry. We've been developing more strain-resistant elastomers that help extend the useful life of the fastener and give us a more compact envelope as needed. And we also have developed new high-performance corrosion-resistant coatings, such as Eon Coat, as shown in the bottom right picture. Eon Coat is a two-part coating that uses a ceramic coating that significantly reduces the abrasion or improves abrasion resistance, and also improves our corrosion resistance. Next, I'll talk about some typical U.S. Transit Agency DF specifications. The common DF requirements from transit agencies will dictate size constraints, spring clip requirements such as the orientation, the type, if they need 0 longitudinal restraint. Also, anchor bolt patterns will be dictated in DF specifications, as well as rail seat height. And the common testing requirements that we will see for DF fasteners will include things such as vertical stiffness, lateral stiffness, vertical and lateral repeated load test requirements, longitudinal restraint, dynamic to static stiffness, and also various electrical requirements such as high voltage withstand, dry and wet resistance, and impedance. So just some basics of a typical direct fixation fastener design. Here you can see a cross section of a typical DF fastener. You see there's a top plate that secures the rail and a bottom plate that secures the fastener to the plinth. The elastomer that is between the lateral walls, that's in a vertical orientation, that dictates the lateral stiffness of the fastener. And the rubber that is between the top and bottom plate in the horizontal orientation, that primarily dictates the vertical stiffness of the fastener. And underneath the fastener, we have these relief patterns that help us fine-tune vertical stiffness and linearizes the behavior of the vertical performance of the fastener. So one of the initial steps in developing a DF fastener is to predict the vertical stiffness in order to hit the target specification. The main factors that go into a vertical stiffness calculation of a fastener is obviously the overall fastener design, how much of the rubber is being compressed, and also the different types of rubber that we use. We have different durometer rubbers in order to hit a target vertical stiffness, and also the elastomer geometry and relief pattern. The formula used on the right is what we typically will use to get a ballpark estimate of what our vertical stiffness is going to be when we start developing a fastener. And from there, we will develop a 3D model and load it into our FEA software, which it will predict our vertical and lateral stiffness, and also let us know peak stresses and strains during the repeated load test, which is a fatigue test that will determine if we can make it through the 3 million cycle. We also perform iterations as needed. If the strain values are too high or the stresses in the plates are high, we'll make design tweaks and run the analysis again. Once a fastener has been developed, we will make the part and run it through the qualification testing. Typical qualification test will take about 2 to 3 months to complete. This table to the right is just a generic qualification test that we will perform to certain agency specifications. They always comprise of a pre-static sequence of tests, which will contain the vertical load, vertical uplift, lateral loads, longitudinal, electricals, and dynamic to static test. From there, we'll do a conditioning of the fasteners, typically a salt spray or a heat age or fatigue cycling, which is the vertical and lateral repeated load test. This test is typically 3 million cycles and takes about 25 days to complete. And then from there, we'll do the post-static tests, which is basically a repeat of the pre-static test to verify that the fastener performance has not degraded. DF qualification testing, we typically will take the most stringent conditions from each agency specification to make sure that we satisfy the most stringent ones. we will run the qualification test in our test lab at Suwanee, Georgia. In our lab, we have 3 test frames with vertical and lateral hydraulic rams that perform the various loading conditions. We have environmental chambers to do the heat aging and different conditioning tests. And then we have electrical test equipment to perform the voltage withstand, the wet and dry resistance, and impedance testing. So looking forward, what can we expect from the DDF fastener industry in the future? Here at L.B. Foster, we're looking at advancements in material technology that allow for higher performance and smaller footprints, such as rubber developments or different coatings to help extend the service life of our fasteners, such as the Eon coating. And also we're seeing agency specifications are evolving to reflect the next generation of direct fixation fasteners. For example, smaller footprints, different loading conditions for high resilient fasteners and things of that nature. And that concludes our presentation. Thank you for your time.
Yes, thank you for listening to our presentation, and we hope you learned something.
Yep. And if you have any questions, please let us know.